Welcome back to the Neural Intel podcast. Today, we're plunging straight into some really fascinating research on robotic hand design.
That's right. We're looking at a specific new hand called RUKA.
And we've got the research paper right here, details the design, the hardware tests, the control system, the works.
Yep, it lays it all out, a proper deep dive into the engineering behind it.
So our mission today is really to unpack those technical details, figure out what makes RUK different, what it means for robotics.
We'll be digging into the unique features, how it pushes things forward in terms of dexterity, but keeping it focused squarely on the tech itself.
Exactly. The engineering, the performance, and for you listeners wanting to stay right on the edge of AI and ML, especially in robotics.
Don't forget the webpage link in the bio. It's got this paper and loads of others.
Okay, let's get started. What was the main motivation here? Why develop RUK in the first place?
Well, the paper kicks off by pointing out, how much progress we're seeing in autonomous robot control, especially dexterous control.
Right, things like sim-to-real, imitation learning,
Yeah,
getting robots to learn complex tasks.
exactly. But there's a catch. The researchers argue that the hardware itself, the robotic hands, are still a major bottleneck.
Ah, so the brains are getting smarter, but the bodies aren't quite keeping pace.
Pretty much. You can have amazing control algorithms, but if the hand isn't capable enough, you hit a wall. Achieving real human-like dexterity is still hardware limited.
That makes a lot of sense. So what's the ideal hand then? What were they aiming for that existing ones maybe lacked?
Well, the ideal hand needs this tricky balance, right? It needs precision for fine tasks.
Hmm.
It needs to be compact, not clunky. It needs strength for gripping and lifting. And crucially, it needs to be affordable.
And that's the hard part, getting all of those together.
Exactly. Existing designs usually involve trade-offs. You optimize for one thing and you lose out somewhere else.
Can you give an example of that trade-off?
Sure, so some hands go for ultimate precision. They put a motor right inside each joint. Direct drive.
Okay, sounds precise.
It can be, yeah, very fine control. But the downside is it often makes the hand bigger, maybe heavier, and sometimes less robust if it takes a knock.
Gotcha. So RUK tries a different approach. What are its core design principles?
RUK is going for a unique mix of three things. Low cost, anthropomorphism, making it look and move like a human hand, and usability.
Usability meaning?
Meaning it's practical for researchers to actually use. Easy to set up, repair, integrate into their systems. The paper even has a Venn diagram showing where RUK sits compared to others like Ellie or Allegro on these points.
And the human-like aspect, how close does it get in size?
It's specifically designed to match the average human hand size pretty closely. There's a comparison figure in the paper showing it next to other common robotic hands, and it fits right in, scale-wise.
Okay, so human form factor, affordable. What were the specific engineering goals they set themselves?
They highlighted three main priorities. First, low cost. The target for raw materials was under $1,300. They even mentioned variants with different motors potentially getting down to $500 to $900.
Wow, that's significantly cheaper than many research hands.
It really is. Second priority was reliability. That means consistent positioning, working for long periods, and being easy to fix if something breaks.
And the third?
Fully open source. The 3D designs, the software, all freely available.
That's huge for the research community, lowering the barrier to entry.
Absolutely. It encourages people to use it, build on it, share improvements.
So you mentioned comparisons to other hands like Ali and Allegro. Let's dig into that. What makes RUK stand out technically?
Okay. Yeah, the paper has a great table comparing UKA to Leap, Allegro, Allegro Zella, InMove, and the Shadow Hand.
What specs are they comparing?
Things like cost, obviously,
Hmm.
degrees of freedom, or DOF, how many ways it can move independently, degrees of actuation, DOA, how many motors drive those movements,
Right.
and critically, the actuation type, is it direct drive, like we talked about, or tendon-driven,
Hmm.
and finally, the open source status.
And where does RUK fit in that table?
RUK comes in with 15 degrees of freedom, which is quite dexterous, but it achieves this with only 11 actuators.
How does that work? Fewer actuators than joints.
Yes, through coupling, which
Yeah.
we can get into, and it uses a tendon-driven system. Plus, as we said, it's open source.
Okay, tendon-driven. How does that compare to the direct drive hands like LAP and Allegro?
So the direct drive ones like LAP and Allegro often get props for low cost and really precise control at the joint level.
But the downsides?
Well, LAP can be quite large, less human-like. Allegro is more compact, But the paper mentions potential issues with motors overheating, and repairs can be tough because everything's integrated.
Right, motors in the joints. And what about other tendon-driven hands, like the shadow hand?
Tendon systems, like shadow hand, can be very anthropomorphic,
Yeah,
closer to human biomechanics because the motors are usually in the forearm or palm, pulling tendons.
that sounds good.
It is. But commercial ones like the shadow hand are often extremely expensive and complex to maintain.
Ah, and the open source tendon options, like InMove?
InMove is much more accessible cost-wise and easier to tinker with. But the trade-off there is often less precise control, maybe less robustness compared to RUKA or the commercial options.
We're also seeing things like soft robotic hands, right? How do they fit in?
Soft hands are interesting. They offer compliance, they can conform to objects naturally, great for certain types of grasping,
Uh,
but they often struggle with precision, force application, and they can be really tricky to model accurately for simulation or control.
and the super complex biomimetic ones?
Those try to replicate human tendons almost exactly. They can achieve incredible dexterity, but wow, they're complex, very hard and expensive to build reliably.
So RUK is trying to carve out a sweet spot then.
Exactly.
Yeah.
Compact, tendon-driven, human-like form, good performance, but keeping the cost down and the design accessible through open sourcing. It's a strategic balance.
Let's get into the mechanics. 15 DOF, 11 actuators. How's that distribution work?
Okay, so the thumb gets 3 dedicated motors, one for each of its main joints. That gives it a lot of independent movement.
Makes sense. The thumb is crucial. What about the other 4 fingers?
Each of the other fingers uses just 2 actuators. And here's the clever part. These actuators are coupled.
Coupled how?
They're mechanically linked to control both the PIP joint, the middle knuckle, and the DIP joint, the one closest to the fingertip, together.
Ah, so one motor action moves both joints.
In a coordinated way, yes. It simplifies the actuation, reduces the motor count, while still getting that curling motion. It's an under-actuation strategy.
Interesting. What about finger spreading, abduction, adduction?
The paper mentions that the splay, moving finger side to side at the base knuckle, the MCP joint, happens sort of passively due to the mechanical design. No dedicated motor for that.
So they focus the motors on flexion and extension.
Primarily flexion, yes. Bending the fingers relies on the motors pulling the tendons.
And straightening them out.
That uses small extension springs built into the joints. When the motor releases tension on the tendon, the spring pulls the finger back straight. Passive extension.
Clever. And the thumb's 3 motors. What specific movements do they control?
They control the 3 key thumb motions.
Mhm.
One for the CMC joint at the base, which allows that crucial opposition movement touching the fingertips.
Right.
One for the MCP joint for moving the thumb towards and away from the palm adduction, and one for the IP joint, the thumb's own knuckle, for flexion extension.
Optimized for grasping.
Exactly. They simplified the kinematics a bit compared to a human thumb, but focused on maximizing functional grasping. The paper details the joint orientations they chose.
And how does the overall range of motion compare to a human hand? You mentioned a table.
Yes, Table 2 compares joint ranges in degrees. And interestingly, for several finger joints, DIP, PIP, MCP, RUKA, actually exceeds the typical human range of motion.
Really? More movement than a human finger?
In some specific joints, yes,
Yeah.
which could potentially be useful for certain types of manipulation tasks.
Okay, let's switch to materials. What's your KA actually made of?
Most of the rigid parts, the skeleton basically, are 3D printed in PLA.
PLA. Standard stuff. Why PLA?
Good rigidity, easy to print, keeps costs down. But for the parts that touch things, the finger pads, the palm pads, they use something different.
Something grippy.
Yeah, a flexible filament called Filaflex Foamy TTU. It's softer, compliant, helps conform to objects. They glue these pads on and add 3M friction tape to the fingertips for extra grip.
So a mix of rigid structure and soft contact points. How's it assembled? Screws, glue.
Mostly screws going into heat set inserts. You melt these little threaded inserts into the PLA parts. Gives you a strong connection point.
Ah, neat. Common technique in 3D printing.
Yeah, and the pin joints for rotation use metal dowels for strength, plus those little extension springs we mentioned for preloading the extension.
And the tendons, what are they?
They use braided fishing line, actually, rated for 200 pounds.
Fishing line. Seriously.
Yep. Strong, flexible, low friction, readily available. It gets routed through the fingers and then through PTFE tubes, Teflon tubes in the palm.
To minimize friction, right?
Exactly. Keep the movement smooth. And they say the routing is adaptable if needed.
Okay, and the motors driving these tendons, we know they're dynamixels.
Right. For the thumb, they use the higher torque XM430 W210T model.
Yeah.
Gives the thumb the strength it needs.
And the fingers.
For the fingers, they use the smaller, lighter XL330 M288T motors. Everything communicates via a USB to serial bridge, standard stuff, and it's powered by a 12V 5V supply.
All right, quite a detailed picture of the hardware. Now, the big question, how does it actually perform? What tests did they run?
They did a whole suite of hardware evaluations, looked at three main things: reachability, durability, and strength.
And compared it against others?
Yeah, they benchmarked against LEP and InMove in some tests.
Okay, let's start with reachability. How well can it position its fingers?
They used a few standard tests. First, the Kapanji test for thumb opposition.
How'd it do?
Perfect score, 10 out of 10, which was actually better than the four-fingered Allegro and Lepier, which scored 9. So really good thumb movement.
Impressive. What else for reachability?
They did a detailed range of motion test, quantifying all the joint angles, like we saw on the table. And they did a big simulation, 250,000 random joint poses, to map out where the thumb could touch the other fingertips.
To visualize the grasping workspace?
Exactly. The results showed a really large area where the thumb and fingers could make contact, indicating it can form lots of different grasps.
Speaking of grasps, did they test specific grasp types?
They did. They used the standard grasp P taxonomy, which has 33 common grasp types. Our UKA managed to successfully reproduce 29 of them.
That's pretty good. What were the ones it couldn't do?
Mostly grasps that need really strong squeezing together of the fingers' MCP adduction or certain complex thumb postures due to its slightly simplified kinematics. But overall, very capable.
Okay, solid reachability. What about durability? Can it run for a long time?
They tested that directly, ran it continuously for 20 hours.
20 hours straight.
Yep. And they reported no significant loss in motor precision. They explicitly state this outperforms Allegro and LEP in terms of continuous operation time.
That's a strong point for reliability. Did they check temperatures, motors getting hot?
They did. Monitored motor temps during 90 minutes of continuous full-range movement. Temperature stabilized well below the max ratings. So thermal management seems okay.
Great. Now, strength. How much force can it apply? How much can it lift?
They did several tests. A pinch test for thumb index finger force, a payload test, lifting a weight with a bag handle until the joint slipped too much, and a slip test, seeing how much force individual finger joints could hold on a scale.
And how did RUKA fare in the strength department?
It actually did really well compared to a cleave and InMove. Table 3 shows the numbers. Significantly higher payload capacity, like 87.5% more than InMove, and much better performance on the slip test too.
Wow. Why is it so much stronger, especially compared to Leap, which uses the same motors?
The researchers suggest it's down to the tendon-driven design. Distributing the load, maybe better leverage. It seems the actuation method itself gives it a strength advantage.
Fascinating. So the tendon system isn't just about form factor, it impacts strength too. Okay, controlling a tendon hand sounds tricky though. The motors aren't right at the joints.
Exactly. That indirect mapping is a challenge. You move a motor pulley, but predicting the exact fingertip position involves tendon stretch, friction, routing.
Yeah.
It's complex.
So how did they tackle the control problem?
They went for a data-driven approach, basically learning the relationship between motor commands and hand movements from data.
Learning, so machine learning involved.
Yep. They developed a whole framework for it. It involves collecting data autonomously and then training a controller.
How do they collect the data?
They used Manuus haptic gloves. These gloves track human hand movements really accurately.
Okay.
They mounted the glove onto the back of RUK. Then they had RUK perform a sort of random walk, moving its motors through lots of different positions, exploring its movement space.
And the glove recorded the resulting hand poses.
Exactly. It captured the fingertip positions, the overall hand pose, and from that, they could calculate the corresponding RUK joint angles for each set of motor positions, generated a big data set linking motor commands to resulting poses.
Clever. Self-exploration mapped by the glove. What did they do with that data?
They used it to train a neural network controller, specifically an architecture using an LSTM long short-term memory network.
LSTMs are good for sequential data, right? Like movements over time.
Precisely. The LSTM processes the recent history of the finger state. Then its output goes to an MLP, a multi-layer perceptron, which predicts the next motor positions needed to achieve the desired movement.
And they train this network how?
By minimizing the difference between the motor positions the network predicted and the actual motor positions recorded during that data collection phase. Standard machine learning training loop.
Okay, makes sense. How well did this learning controller actually work? Did they test it?
Oh yeah. They compared their LSTM plus MLP controller against other methods. a simpler MLP-only controller, a K-nearest-neighbor approach, and a search-based method.
How did they compare them?
Using two test sets, one called human validation, where a person wore the glove and made movements, the other, robot validation, where the glove was on the robot and fingertips were moved manually.
And the metric was?
How accurately the robot could reproduce the recorded fingertip trajectories using the motor commands predicted by each controller. They measured the position error.
What were the results? Did the LSTM approach win out?
It performed really well, especially on the human validation set. It seemed better at generalizing to those more natural, complex human poses compared to, say, KNNN.
So the memory aspect of the LSTM helped.
It seems so. Capturing those time dependencies appears crucial for controlling this kind of tendon system accurately for human-like motion. The simpler MLP and search methods didn't do as well.
That's a key finding. Did they also check if this controller works on a different RUKA hand? Since it's open source, people will build their own.
Great question. Yes, they did. Transferability is crucial. They built a second RUKA hand. They developed a quick auto-calibration script first, just to estimate the motor ranges on the new hand, account for slight build differences. Then they ran the robot validation tests, again, using the original learned controller.
How close was it?
The average fingertip position difference between the two hands was only about 3 millimeters.
Only 3 millimeters. That's pretty good.
Yeah, it suggests policy learning, using imitation learning.
Teaching the robot by demonstration.
Right. They used a framework called HUDOR. Applied it to tasks like flipping a cube in the hand or picking up bread and dropping it.
How did the learning work?
They trained a residual policy. It learned small adjustments to the motor commands based on demonstrations, refining the movement. And it learned relatively quickly, like converging in under an hour for these tasks.
So RUK can learn manipulation skills directly?
Yes, and they showed online fine-tuning could improve the learned trajectories even further. It really positions RUKA as a platform for research into robot learning for manipulation.
Okay, let's wrap things up. What are the big takeaways here, and what are the limitations?
Well, the big takeaway is RUKA seems to successfully hit that sweet spot. Dexterous, anthropomorphic, but also low-cost and open source. It tackles known limitations of other hands.
But it's not perfect yet. What are the downsides?
They point out a few. Relying on the expensive Manuus glove for controller training is one barrier. Lack of tactile sensing is another big one. No sense of touch.
Right. Crucial for delicate tasks.
Definitely. And the current design lacks active finger spreading, abduction-adduction, though they plan to add that later with a compliant joint.
What about things breaking? Maintenance?
They mentioned two main failure modes. The plastic gears and the cheaper finger motors might wear out over time. Using metal-geared ones is an option, but costs more.
Okay.
And the base knuckles, MCP joints, could get damaged by impacts. But they stress that repairs are quick, like under 20 minutes, because the design is simple and modular. And being open source means users can modify it, maybe use tougher materials if needed.
So overall, a really interesting development in robotic hands. This deep dive into RUKA has shown a clear focus on bridging that gap between advanced capability and practical accessibility for researchers.
Absolutely. The technical journey from the tendon actuation choice, material selection, right through to that data-driven LSTM controller, it highlights the clever engineering needed to mimic human dexterity affordably.
And those performance tests give concrete evidence of its capabilities compared to other well-known hands. It's not just theoretical.
Right. The reachability, surprising durability, the strength tests, they provide solid benchmarks.
Plus, seeing it used for teleoperation and learning complex tasks like cube flipping really shows its potential as a research tool to push robotics forward.
Exactly. It's a platform to build upon.
Hopefully, this exploration gave everyone a good technical grounding in what RUK is all about. It certainly feels like a significant step. What aspects stood out most to you? Maybe the cost-performance ratio or the open source approach?
For me, it's probably that successful blend of the tendon-driven mechanics with the learned controller. Making that complex system work well is impressive. It really opens doors.
Yeah, definitely a lot to think about. It makes you wonder what the next iteration might bring, maybe integrated sensing. It's such a fast-moving area.
For sure. And RUK feels like a really solid contribution to that progress.
Don't forget, listeners, you can find the full paper linked on our webpage if you want even more technical grit. Thanks for joining us on this deep dive into the Neural Intel podcast.
We'll catch you next time with another look at the cutting edge in AI and ML.